Okay. I just started recording. If you weren't here for the beginning, we first did a problem that was on the practice problems for Unit 12, and we saw something very strange. I think it's very strange. We saw that when we drew the 1-2 product and the 1-4 product, and we did our analysis, the kinetic product is always the 1-2 product. So I'll label this always 1-2 kinetic. The thermodynamic product actually is chosen for the more stable alkene. Typically, the 1,4 product is thermodynamic. It's the more stable one. But in this case, because the 1,2 product is tri-substituted, and the 1,4 is di-substituted, again, this product is also the thermodynamic. That's a little bit tricky. So it doesn't matter what the temperature was actually. I could have run this on cold temperature or hot temperature. The major product is going to be this one because it's both the kinetic and the thermodynamic. Because that was a little bit unusual, and I want you to understand the differences between kinetic and thermodynamic, I propose a new diene, and this diene right here. If you're doing a reaction on this double bond right here, then your 1-2 product would look like this. 1-2 meaning the 2 has to corner. Okay. Again, 1-2. If you want to draw like on a scratch sheet of paper the carbocation, just visualize this molecule with a plus charge right on carbon number 2. That's a allylic, a little carbocation. Plus, so how would I do this without doing a lot of scratch work? Well, I pretend there's a carbocation carbon number 2, and I shift the double bond to the left, and I get this. But when you do resonance and you shift the double bond to the left, the carbocation now ends up on this carbon. That's where the chlorine's going to go. You could double check yourself, because when you number the chain, right, from the original, all the sp2 carbons, 1, 2, 3, 4, you get the 1,4 product. So no debate, 1, 2, 1, 4. No debate. This is kinetic. 1, 2 is always kinetic. What could be debatable is which one is thermodynamic, because it's based on the stability of the double bond. This double bond is di-substituted, right? Because on this carbon you have 2 hydrogens, but on this carbon you have 2 R groups. One going up, one going down. Di-substituted. Oh, look at this. You have this carbon has 1, 2 groups. This carbon has 2 groups again. This is tetra-substituted. This is definitely the more stable product. By far, the more stable product. Okay, I have 2 products. Typically, I'm going to ask you, if you have a mixture, what's the major product? If there is a major product. You might be tempted, right, to circle the thermodynamic because it is so stable compared to this di-substituted alkene. The thing is, oh, we're at room temperature. Oh, that's good. At room temperature, you do favor, what did I write here? Room temperature or higher, you do favor the thermodynamic. So this is your major. Okay, so we are favoring more stable product. But what if we are doing this at very low temperatures? HBr and minus 80 degrees C. Okay. Yes, I do get the same products, except I have now Br. But this is your major product. Your 1, 2, the product just makes faster. The product makes faster. So that's unusual. That's actually not unusual. That's kind of cool. That we could favor the less stable product, right? We could favor the less stable product by running this reaction at so low temperatures that we don't give the reaction a chance to equilibrate and form the more stable product. If you think about it, we have one starting material, okay, one starting material. And whether you make the 1,2 or 1,4, right, you are hitting an intermediate. This is your carbocation. Your carbocation has resonance. I understand that. But what do you know about resonance? It's the same molecule, just two different representations. So you have that, and let's double check my work. You have this. That is represented by the same hybrid structure. So I'm not going to have two lines representing the two resonance structures, right? It's just one hybrid structure that I'm not drawing. It's the one with the dotted lines. Look at this. Look at my pink line. A pink line goes now like this, and I end up here for the products. Okay? And then look at my green line, or what color do I want to use? Let's see if purple works. Look at my purple line. Bigger hill, but lower valley. Which color represents the pathway of the kinetic? Which color represents the pathway of the thermodynamic? Did I say that right? One is the kinetic pathway and one is the thermodynamic pathway. Think about your temperatures and think about your products. One is made faster, one is more stable. So what do you think is faster? The pink line or the purple line? Yeah, because it has a lower activation energy. So the pink line is the kinetic. It's the one that's definitely made faster. But it's not favorable in the sense that it's not lower in energy. So think about this. You run the reaction and you get a lot of the molecules at kinetic. If you're at low temperature, you're good. That's it, kinetic. But if you're high temperature, you could go backwards over this hill and start over again. And it's going back and forth. And every time you go back and forth, you get a little bit more of the thermodynamic. The thermodynamic is so low in energy that even at high temperatures, you can't get over the hill backwards. This hill is stupendous. It is so high, you can't go backwards. So you actually get trapped. So both of these is, you could get trapped. If you're at low temperature, you get trapped in the kinetic. If you're at high temperature, you could equilibrate, but you'll still get trapped now at the thermodynamic. So this is the thermodynamic. Okay. What happened? What happened here? What happened here was both lines, the kinetic and thermodynamic, ended up in the same place with the same height. So there's no difference between the kinetic and thermodynamic. But in this case, there is. Okay. All right. So that is quite a bit for kinetic and thermodynamic. Let me take a look at the group chat. If there aren't any more questions about this, then we're good. But if you do want to practice more, let me show you. I mean, maybe we can do this in our heads. Maybe we can. Where is it? Oh, here it is. Maybe we can talk this through without having to actually write it down. Because look at this one here. Okay, it's still a diene. Okay, we can still get 1, 2, and we can still get 1, 4. So I would expect two products here. What's the easier to draw? The easier to draw is the 1, 2, right? Because you're not doing any resonance, so your second double bond is not shifting. Remember, for 1, 2, we just put the chlorine right here and keep this double bond right here. Same thing for here. If we do the 1, 2, the chlorine will go right here. Okay, allylic. Now the 1, 4, right? Can you imagine the carbocation right here on this carbon here? Let me make this bigger if possible. For the 1, 4, your initial carbocation is here, but for the 1, 4, you resonate and you bring this double bond right there. Ooh. You see, if I put the double bond now right here, that double bond is tetrasubstituted. Okay, so definitely that would be the thermodynamic product. And the chlorine would go here now. But we have very low temperature. So we are going to favor the kinetic. So what does a kinetic kinetic answer look like? Again, here we are. Hopefully you can see that. So we were discussing this problem here. Okay, good. This is a kinetic. The thermodynamic is definitely different because see how it's tetrasubstituted? This is definitely the more stable product. But because at low temperatures you get trapped, right? You get trapped in that valley and you can't go back. You're going to favor the kinetic product. We got trapped because we don't have a high enough temperature to equilibrate. Oh man. So this one, I know it seems that the majority of times that we have the kinetic and thermodynamic identical, but that's actually pretty rare. But here we have another kinetic and thermodynamic where it's both the 1,2 product. So you see how it's a thermodynamic product that kind of jumps back and forth. It just depends on which double bond is more stable. Kinetic is always 1,2. Kinetic is always 1,2. Okay. Why did I give this? So this one's not symmetrical. Let me see what that looks like. Oh, because I gave you the products. Okay. So, do you see what happens when it's not symmetrical? So I would never ask you to draw the products of a HX addition if the diagonal was not symmetrical, because, well, we didn't have a lot of time to discuss this, but also we get 4 products now. 1, 2, 3, 4. Because we got 2 products from this double bond, right? The 1, 2 and the 1, 4. And we get 2 products from this double bond, the 1, 2 and the 1, 4. Can you tell, where did these 2 products come from? They came from this double bond right here. This is easy because see, this is 1, 2. Okay. Now, why did I say this was the major? See, it's at room temperature, so I'm really trying to pick, yeah, the most substituted alkene. So it's right here again, tri-substituted. Okay. This is also the 1, 2 product, right? Because hydrogen goes here, bromine goes here, 1, 2. The good thing about this problem is that I'm not really asking you to draw me the products and analyze it. I'm just telling you, how did you get this major product? What is the mechanism? Okay. What is the mechanism? And then this one also. I think I asked you for the minor product. What is the mechanism? Right, so that is HX addition to dienes or conjugated dienes. Let me take a look at the chat. Reaction 12A, whenever you get it. Oh, so I think this is reaction 12A. Reaction 12A is HBr or HCl addition to conjugated dienes. Let's go back to the notes. Let me just verify that. Yeah, 12A. Yeah, 12A. What's not in the notes that I added here, which might help you understand better kinetic versus thermodynamic, is that reaction coordinate diagram, the hills and the valleys. The hills and the valleys. Interesting. Okay, so good. Are there any? You know what I wonder actually? If I draw the reaction coordinate for this problem here, and I know that the kinetic and thermodynamic are ending up in the same valley, where is this guy? This guy has to be more unstable. So I would expect it, higher, right over here, and a higher hill, right? Because it's Would I expect a higher hill? Um, that I don't know. But I do know for a fact that this alkene is less stable. So it would have to be higher than the line representing this product right here. It's lower also, right? This is kinetic. So this also has to have a bigger hill. Bigger hill. Very unusual. Let me just do this because I'm just curious. So here we have the valley for the carbocation. And we do have one product, kinetic and thermodynamic, so I'll draw it down here. And this weird one, right, it's neither the fastest, so it's not the fastest, the hill has to be higher. But it's also not the most stable, so its endpoint has to be also higher. Not great, right? There's nothing going for this product. It's neither the fastest nor the most stable. There's a big difference between that and this reaction coordinate here. All right. Um, okay. What other questions do you all have? Just speak up. Any question is fair game, or I'll answer. I'll try to answer any question you all have. Yeah. Let's see what are some tricky ones. Give me 1 second. Where am I? Okay, Diels-Alder. Um, hopefully you can see my PDF. So we have a simple Diels-Alder on the screen right now. And how can we complicate things? We can complicate things by adding groups anywhere on this 4-carbon chain or anywhere on this 2-carbon alkene. So here's a little more complicated, but again, you're just making the 6-membered ring, so maybe that's not as complicated as you want to practice. So one variation is that if we use a triple bond as the dienophile, just remember that when you go from a triple bond and you do the Diels-Alder, you go down to the double bond now. Normally you would go all the way down to the single bond, right? Because we start out with a double bond. So that's one variation. The other variation is what if your diene has a bridge, right? This is weird. We haven't seen this yet. So there's a bridge here. How do you draw that? So how do you draw that? There are two ways. You could start out with a 6-membered ring. Okay, this is a 5-membered ring. What are you talking about? A 6-membered ring? Well, look at all your answers. All your answers have a 6-membered ring with a double bond on the left. 6-membered ring, double bond on the left. 6-membered ring, double bond on the left. 6-membered ring, double bond on the left. This carbon here, we could call it carbon number 5 for this 5-carbon ring. You got to put that somewhere. It's connecting the 2 red dots. So the way I do it is I draw a little bridge here, like this. Okay. But on the textbook, this is kind of hard to draw if you're trying to keep all the bond lengths the same. It gets kind of crowded. So in the textbook, they look at it from the side and see this bridge right here. They actually drew it like a bridge, like it's going over the water. See this double bond here? That's this double bond right here. Okay, so that's one variation. Let me show you, and then we'll do one together. Let me show you the hardest one. I think I put it here. This one, right? The only reactant you have here is heat. So you're not doing HBr, HCl. You have an aldehyde, but we're not doing aldol. We're not doing aldol condensation. We got to figure out what the heck we're doing here if we're just using heat. Well, that's Diels-Alder. Okay, so for a Diels-Alder, what do you need? You need a diene, and you need an alkene or a triple bond. Here's your diene, right? Here's your diene, and here's your dienophile. So they happen to be in the same molecule. Let me go through this one, and then I'll make up one. This is probably the most challenging one. But let me show you how to do this from the answer key, and then I'll give you a new one. So on the answer key, okay, remember that. I got to figure out how to make it look like this. How to make it look like a diene that I'm used to and a dienophile that I'm used to. So do you see how this letter C is kind of facing this double bond here? Well, I could do that with that long, with that long chain. Let me find it. Right? Okay. Hopefully you can see that. I'm always doing red dots and blue dots because for Diels-Alder, red connects to blue. Here, red connects to blue. Right here, red connects to blue. Right here, red connects to blue. Right here, red connects to blue. So if I can find my reds and blues, okay, my diene is right here. I'm going to twist this bond right here to make it look like a C. And then it does turn out very well that if you kind of twist this bond right here, you could get the double bond to face it. So I'm doing just a regular mechanism with Diels-Alder, the 3 arrows. The thing is, you got to connect red and blue, and you got to make a 6-membered ring. So when I drew this answer, I didn't draw carbon 5 and 6 right away. I didn't draw carbon 9 right away. I only drew this part, the 6-membered ring with a double bond. When I follow the numbers, the red dot connects to the blue, the 4 connects with the 7. Where did 5 and 6 go? 5 and 6 are connecting 4 and 7. So that's why 5 and 6 I put up here. 4, 5, 6, 7. So what is this bond between 4 and 7? That is the normal single bond made in the Diels-Alder reaction, right? This is bond 4 and 7. 4 and 7. This is bond 4 and 7, right? 1, 2, 3, 4, blah, 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 7. Okay, if there was 5 and 6. But you're always connecting red and blue. So that, that 6-member ring is always there. You just have to figure out where the other carbons go. So that is, we could call that an intramolecular Diels-Alder. I can ask you also, we're not going to do this right now, but I could ask you, if I give you a product like this, what did the starting material look like? So the thing is, in our template, you just cut between the red and the blue. Cut between the red and the blue. Cut between the red and the blue to get the starter material. Cut between the red and the blue to get the starter material. Cut between the red and the blue. Oh, I'm not cutting between 5 and 6. So take an eraser, erase this bond and erase this bond. You just have to remember that it Diels-Alder is a diene plus dienophile. So you got to make your red dots look like the diene when you go backwards. And you got to make your blue dots, right? Your blue dot portion of the molecule look like the alkene. So that's, again, one of the more complicated ones. Let me make up a Diels-Alder product, Diels-Alder reaction, and you'll draw me the product. Oh, this is going to be interesting. Yeah, let's do. You're not going to like this. This over. This is not bad, and this is not too hard. So how about this? First of all, why am I decorating it like this? I think I mentioned on the video, to speed up a Diels-Alder, you want electron-rich groups, electron-donating groups on the diene, and electron-withdrawing groups on the dienophile. You want this to be electron-rich, and this to be electron-poor. But that's not the big deal, right? The big deal is now, how do you draw this product? So there's an issue here. The issue is I don't have a normal diene, right? I have a cyclic diene. I have a bridge. So let me get you started, and then I'll give you a couple minutes, or a minute and a half to do this. The bridge is between what? The two red dots. So this, when you see that, you're going to draw me a product, a product that looks like what? A product that may look like this, right? Side view. This. Probably not something like this, right? See, neither of these have a bridge between the two red dots. Okay? If you want to draw it kind of flattish, then what could you do? You could draw it like this. Like this right here, right? This is a bridge, but I drew it looking from the top. Okay, so you should understand these two are identical, right? But I think I like the idea. I like the drawings that are on the side view, where you have the bridge kind of jut out over the water. Okay, so let's go back to that problem. Test yourself. What is the product here? If you're worried about stereochemistry, endo and exo, I may ask you. You could draw either. I'm probably not going to ask you to draw both endo and exo, but I may ask you, is your product that you drew endo or exo? And that will require you to identify, what did you draw? Did you draw the endo version or the exo version? I'm going to shut up and give you a minute and a half to finish this, fill in the product. Okay? Be honest with yourself. If you're having trouble with this, my question for you is, did you draw blue dots? If you did, hopefully that you're not having any troubles. If you're still having troubles, okay, if you're still having troubles, are you looking at the template, right? Are you looking at some templates that show you how to draw this? Let me draw you, if you're not having trouble with this, don't draw this. Or even if you are having trouble, don't draw this. A good template for this kind of problem would be this. Why would I choose that? I chose that because your diene would have 2 carbons for the bridge. See how these 2 carbons are up here? Those 2 carbons are connecting the 2 red dots. So your 2 red dots are here and here. Plus your dienophile right there. So it's a very plain dienophile. Okay, this is my template. Okay? Just like we had a template for just that plain 6-membered ring for the product, this one I want in my head because I'm going to try to draw it from the side view. But look what I have. I have an oxygen right there. Okay, so I got to consider that. I have a bunch of junk on the blue dots, so I have to consider that. Now, if you're not understanding what this picture represents, let me try one more drawing. Okay, I'm going to try this as neatly as possible. Carbon number 1, carbon number 2, carbon number 3, carbon number 4 up here. Then we have an oxygen. Then we have another carbon here. So look what I'm going to do. I'm going to indicate that this bond is behind, okay? Behind this bond on the front. So basically I have something like a blue bond in the front and a black bond behind it. Okay. So without this gap, maybe you're confused and think this is a carbon here. That's not a carbon. It's just an overlap of two bonds. Where are your two red dots? Your two red dots are here. A six-membered ring, six-membered ring. I already shifted the double bond because that's where the double bond goes when you do the reaction. Right? It goes away from here. Well, heck, if you're really having trouble, go ahead and draw your mechanism. Okay, great. So you notice that both of these red dots do not have a double bond anymore. You use this double bond to make a bond to the blue, and we shifted this double bond to put it right here. What about your other? Without drawing any connections, my dienophile is actually floating or coming from underneath. And I have this groups. I have this OBT, and I have this OBT. Now, I know I drew it kind of weird. I'm trying to draw these going down. And you'll see why in just a sec. So there's my connection. The two bonds that were made. I made this bond here, and I made this bond here. I may ask you, did you draw the endo or the exo? See, these are on the same side. So either they're both going to be under the bridge, or they're both going to be over the bridge. When they're both under the bridge, you call it endo. And endo is actually the major product. Okay, major product. How do I represent, though? Because it's still hard to tell. Am I really under the bridge? Well, you know that both of these carbons have a hydrogen. This is not necessary. If you draw them kind of downwards, I will understand that you want endo. But in literature, just to emphasize that fact, these are tetrahedral carbons. And if you could see this in 3D, see those two hydrogens are pointing up. And these two carbonyl groups are going downwards. What if you want to draw it? What if you want to draw it the other way? What if you want to draw the six-membered ring first, and you want to draw it flat? We could do that as well. But you notice how I made this a little bit wider? I have to make this wide because I know I got to fit a bridge somewhere in the middle. Okay. I'll take care of the bridge in just a bit. But look at your dienophile. Your dienophile looks like this. It is true that when you draw it this way, you're not showing any stereochemistry. Okay, so and I didn't really emphasize that on the videos, so I'm not going to ding you if you don't draw wedges and dashes here. Okay, technically, right? See how this bridge is going up, and these groups are going down. Technically, I would draw these both dash away from us. Now the bridge has to be towards us, right? The bridge has to go in the opposite direction. So this is takes a little bit of finesse, but maybe you could draw something like this. Okay, can you tell that this is a two-atom bridge, the oxygen and the carbon? That's one way to do it, and that's why I don't like drawing it this way, because if you have two atoms between the two red atoms, it's kind of hard to show that angle, enough of an angle to understand that this is a carbon right here also. Okay. But if you can indicate that, then this is perfectly fine. Okay. If you want something maybe just slightly harder, okay, just slightly harder, I'll give us the same diene, okay? So I'm not going to do this with you. But what if I gave you this? Oh, this is interesting. Those of you who are becoming, I don't know, general practitioners or physicians, you got to, analyze the whole patient, but you can't get distracted, right? Just you can't get distracted by ailments that don't really contribute or aren't really coming from the, I don't know, the main disorder or the main disease that you're trying to cure. We know that this is the diene, right? It's conjugated. So this has to be the dienophile. Don't get distracted by the carbonyl groups. Heck, don't get distracted by two double bonds. You know what happens. You're only going to use one double bond to do the Diels-Alder. Okay. So go ahead and draw your mechanism, 3 green arrows, and you'll draw the product. Okay. Go ahead and copy this because I'm not going to be doing this with you. I want to try to answer any more questions that you have. It seems like we've focused mainly on Unit 12, right? The addition to conjugated diene and Diels-Alder. Afterwards, if you want to go over with Jose or your classmates what you have here, then you're perfectly free to do that. But are there any questions for Unit 9 and Unit 10? Remember, Unit 9 is kind of big. It's the enolate, the aldol and Clayton. But it was our first unit, so maybe you've practiced that plenty of times and you're not too worried about that. Unit 10 were the amines, the Gabriel synthesis and the Strecker synthesis. Plus what else? I mean, let's jot down, so you'll save this for later. Unit 12. We did go over the roadmap for Unit 10. Amines. We did go over the roadmap for amines, but just for a quick refresher, to organize your thoughts, you have the Gabriel, you have the Strecker. We have some review reactions to make primary amines and secondary amines and tertiary amines. But what was the other newish reaction? I say newish because it's really reactions that we've seen already, but combined in a different fashion. And I'm messing this up. We actually had 3 more reactions, right? We had imine. Sorry about that. Imine formation and enamine. Okay, now I'm ready. There was a 5th reaction. What was that? A, B, C, D, E. Right? What reaction are we missing? You can't forget this one. This one is definitely going to be a fill in the product reaction. Remember what it was? Reductive amination. Why do I say this is newish? Because what is reductive amination? It's really just an imine formation, right? Imine formation, then CN attack. Oh no, not CN attack. Imine formation, then reduction. All right, you have a day to study. Let me give you an example. If I want to make an imine, I probably should start with a carbonyl group. I'll do the aldehyde. If I want to make an imine, I should have a primary amine. So let me give you this primary amine. The reduction, not sodium borohydride, okay, which would work, but there's a fancier reagent that people use. It's close. It's sodium cyano borohydride. The intermediate that you get for this, you do get the imine. So let me draw that first. You see that? Let's put the group on the right where it's less crowded. And then your final product is reduce that. Okay, don't draw the H. If you do, you're going to have to draw two H's here. Because of the reduction delivered a hydride to this carbon right here, as you would expect. You have two hydrogens here. Reductive amination is a good way to make secondary amines. Can you make tertiary amines? You wouldn't be able to make a tertiary amine because you're not making an imine, right? If this was a secondary amine and you have another group here, remember you would make the enamine, right? You would make the enamine instead. If you look on your Friday notes, I think we had the roadmap include imine and enamine formation. That should be you should have notes, or you should have study aids for those 5 amine reactions. All right. Are there any questions now? If not, well, we could go. We could end the Zoom meeting a little bit early, and you guys can go practice. There really is no question. Yeah. So the Strecker, pretty simple. If you remember one thing, and that one thing is that, well, two things. Strecker, you're making an amino acid usually. The second thing is the R group of the amino acid. Let me scratch that. The alpha carbon of the amino acid is the carbon of the aldehyde in the starting material. So let's make up an amino acid. H2N. Remember, an amino acid is an alpha amino acid is you have always the amino group and the carboxylic acid, and you have this R group. And I'm going to make a crazy looking R group. Okay, maybe not too crazy, but let's say we have this ester or ether. This is what you do. Find your alpha carbon. You're going to make an aldehyde, or you're going to use an aldehyde. That carbon right there is this carbon right here. Okay. So you might ask yourself, how can that be? Like, how do we get this carbon? This carbon comes from the cyano group, the cyanide. But don't worry about that. I'm not going to label this as the alpha, but I will label it as will become the alpha. So what do you have to match? You have to match the R group. So the dot is right there. We have a carbon. That next carbon has a methyl group, a CH2 group. That CH2 group is connected to an O. So there's a CH2 connected to an O, and then that O is connected to methyl. If you did this correctly, okay, your starting material for your Strecker has to be an aldehyde. Has to be. See this hydrogen right here? That's actually the alpha hydrogen right here. Okay, so it has to be an aldehyde. And your aldehyde now should be 1 carbon less than your carboxylic acid because your aldehyde is only taking care of those carbons, the ones that are visible. So look at your target. 1, 2, 3, 4, 5, 6. Look at your starting aldehyde. 1, 2, 3, 4, 5. Okay. That's the hard part. Coming up with your starting material aldehyde for this Strecker. What are you doing in the Strecker? In the Strecker, you are making the imine. This is interesting. So what are the reagents? On face value, like if I have only this, wouldn't you expect a nitrogen an imine right here, a nitrogen hydrogen carbon double bond. So where's this carbon coming from? That carbon is coming from the cyano group. So you could do KCN, HCN, but I'm going to do HCN, number one. That takes care of putting the nitrogen here and a CN group also on the dot. But I have to hydrolyze that CN group to make it a carboxylic acid. That's why your second reaction should be hydrolysis. I think I normally put heat. Sometimes I put H2O and HCl. Now this reagent here, there were a couple ways that I showed you how you could get those reagents. Here it is. So I did do it exactly how I did it on the video. NH3 HCN right there. Okay. But you could also do it this way. I have it. In practice, I don't like using hydrogen cyanide because it's a gas and it's cyanide, right? You're gonna gas yourself. Okay? So typically, you take the salt and you do this in a hood, and you make the hydrogen cyanide in the flask. You don't transfer it from a gas canister. And to be able to do that, these are the ingredients. So it doesn't matter if you use these two or if you use these two. Okay, just be super careful if you're going to do this in real life. But what's happening here? Let me put here or, just in case you see it on the exam, NH4Cl plus Kc. What you're making here in the first reaction is this, the imine, NH2, that, oh, no, we have CN. The CN has to attack also. We actually get a lot accomplished in the first reaction. NH, technically because you're going to make acid, you're going to have NH3, but here you have the C triple bond N. And then this is your alpha carbon. The hydrolysis, you understand that you cut right here. I do prefer that you keep this protonated because the last thing it's seeing is acid, and then you have this. Okay. So that is the Sprecher. The two things. The first one is easy. You're going to use this to make amino acids. The second thing is the alpha carbon of the amino acid is the carbon of the carbonyl of your aldehyde. So that hopefully gets you quickly to what aldehyde you want to make, or what aldehyde you want to use. And then just be confident that when you do finally add this carbon from the nitrile, that will be the carbon of the carboxylic acid because of the hydrolysis. All right. That is the Sprecher. I don't know if Jose is available later tonight. I am. I have. I'm gotta go. I think. Mm, I don't know if this video is gonna make it onto Moodle. I'm gonna try to process it, but processing takes a while, and I won't be at a computer in about 10 minutes. So hopefully you've been taking notes. Are there any last minute questions? Really? Yep. Yep. Uh-huh. you would end up with the same product. As long as you end up with the correct product, I don't care how you draw it. Is that what you're asking? I think in the products where I draw it, where the bond is going straight down, what the strategy there was I was drawing the starting material exactly the way it looks like. I wasn't twisting the starting material because I keep saying that your enolate looks exactly like your starting material. All you have to do is make a bond from the alpha carbon. So let's see. Let me show an example. So sometimes I do, twist the starting material so I can attack towards the northeast. Like, let's see, like over here, right? So I twisted this around so the alpha carbon is right here, and I go towards the northeast. But what else could I have done? I could have just drawn this molecule right as is, and then just draw a bond from this alpha going up. As long as that alpha carbon is hitting this carbon, and I have all of this group, it doesn't matter whether I draw the bond going to the northeast, or whether I draw the bond going straight north, or let's see, for this one, I could have drawn it going straight down to the south, right? As long as it's hitting this dot, and I'm copying the rest of it um, perfectly, right? Don't forget that when you attack the carbonyl group, right, this carbonyl group becomes the OH. So that's one way. Like over here, you have some attacking to the northeast because I twisted this molecule. But what could I have done here? Look at my mechanism. You see how my mechanism, that bond is going straight down? You see, this is the alpha carbon, and instead of drawing it to the northeast, you see how I'm drawing it straight down? Yes, yes. So do you realize that these two molecules are identical? Yes. So it doesn't matter. I can figure it out what other ways it could look like. Really, all I'm looking for is does it look like you connected an alpha, the correct alpha, to the correct dot? And for this aldol, I expect an OH on the dot. So again, if you label this alpha and the dot, the bond is going straight down now. But again, why would I do it that way? I did it that way because see, the top half of the molecule looks exactly like this. So I'm not doing anything special when I draw it. I'm just drawing the molecule again, and then I draw the bond. Um, the thing is, the way I taught it, and I wanted you to memorize that this is a beta hydroxy ketone, it just looks better to me where you have the hydroxy and the ketone like side by side. But I have the same thing right here. See, this is alpha, this is beta. So this is a beta hydroxy ketone. It's just not on the horizontal line, it's going down. So again, so that's why there are good reasons to draw them either way, right? There are advantages to drawing it this way, but there's also advantages to draw it this way. All right. Um, so I gotta go in the last, 12 hours, 12 hours, more than 12 hours before exam. Go ahead and polish up uh, some concepts and some reactions that you are not sure of. Definitely try to do all the practice problems. Um, and then, you know, see if you can see Jose. So the forum, keep putting questions. I may answer some questions on the forum like early tomorrow morning. I did have a cutoff though in terms of extra credit, but maybe I'll extend that extra credit till later tonight, and I'll just double check the forum again and add those extra credit points. I think you could get a maximum of 4 points extra credit by putting up 4 questions and or comments on the forum. All right, and then as normal, get organized, have your notes somewhere, spread out on your desk. I think that's a strategy for a lot of people who are getting, very good grades. They know where to find the answer. Not that they need that, but they know how to double check answers in a very efficient manner. Because I feel like when I look at some of the exams, I could tell that from the erasing that you had the wrong answer at first, but then you had some time to look up, some techniques or look at an example, and then you changed it. So I'm fairly pleased that that a lot of you know how to get the correct answer eventually using your resources. All right, I'm good for now. If there are any more questions, go ahead and see if you could email Jose or put it on the forum. I won't be able to meet again until I see you on the exam tomorrow at 10 a.m. All right, so if you're good, you can go ahead and uh, leave the room. If you have any questions, maybe not about material, but any other questions, you could hang back for a minute and just either put it on chat or just let me know. Right, but for most of you, I'll see you on Monday. All right.